Okay, so good afternoon, everyone. Yeah, it looks like I am the last presenter on the last day of the conference, right? Yeah, it's a really honor to have the chance to share my work at the top-tier conference ISCA. As the session chair kindly introduced, I focused on designing hardware accelerators that efficiently learn machine learning and security algorithms. Today, I will introduce a new area and energy-efficient hardware architecture for accelerating a machine learning model called NeRF. Have you heard of NeRF before? If you are in computer graphics or vision, it might sound familiar. NeRF is a model that learns from multiple 2D images taken from different angles and reconstruct the 3D scenes using a neural network. In other words, after learning from a set of photos, the model can generate the view from any camera position or viewing directions. In traditional 3D rendering, as shown in the figure, as shown in the diagram at the bottom right, its pixel is processed through the complex graphics pipeline. Even a small change in the camera viewpoint means recalculating all pixels, considering geometry, lightning, and materials. But with the NeRF, if we provide the parameters of a new camera pose, the model can generate the corresponding view using what it has already learned. Because of this, NeRF has recently gained a lot of attention in VR and AR applications. So why is NeRF getting so much attention? Because it can generate scenes that are much more realistic than traditional rendering methods. On the bottom left here, you can see an example rendered by Google's NeRF model. It looks very close to what we see in real life, right? This ability to generate photorealistic scenes is one of the main reasons NeRF is getting so much interest in VR AR. But there's a question. Can NeRF actually be used in VR AR applications? Before we answer that, let's think about what matters in VR and AR. Okay, picture it. What if the screen response is slow? If the visual can't keep up with the user's head movement, the sense of immersion drops, right? And if the hardware can't update the image fast enough, you got motion blur, as shown in the figure. This not only breaks the realism, but can also cause user discomfort like dizziness or nausea. That's why real-time scene rendering is so critical in VR and AR environments. The problem is most NeRF models can't meet this real-time constraint. Even when running on powerful desktop GPUs, which are stronger than mobile GPUs, they still fail to render fast enough. You can see the rendering latency in the figure on the bottom left. So clearly, using NeRF in real-world VR AR requires further work. On top of that, VR AR devices are small and battery-powered, right? Sure, some current devices are still powered through cables, but based on our survey, most commercial battery-based VR AR devices are designed to stay under 10 watts to ensure at least 4 hours of usage. Also, the chips have to fit inside a very small form factor, right? For example, according to AR glass specifications provided by Texas Instruments, some high-end AR glasses require the chip to fit just 10 square millimeters. In contrast, conventional GPUs that are used for rendering typically exceed both the area and power limits. So if we want to use NeRF on immersive device, we clearly need a new accelerator design that's both area and power efficient and still fast enough to handle real-time rendering. That's exactly where our work began. To design an efficient NeRF accelerator, we first need to understand how NeRF behave in real VR AR use cases. Okay, let's assume a scenario where a NeRF-based application is running directly on a VR AR devices. In many cases, the app is downloaded from the cloud and runs locally on the device. But here's the catch. The device has no idea which NeRF model is inside the app. That decision is made by the application developer, who might use any model depending on the task. And to make rendering faster, developers often apply techniques like quantization or sparsity. So, from the hardware's point of view, it needs to handle many different types of NeRF models, such as with each with different levels of precision and sparsity. We also profiled the performance of many different NeRF models, and what we found is that both models have a common bottleneck, that is JAM and JAMV operations. You might wonder, well, there are already commercial accelerators for JAM and JAMV. Can't we just use them? But in practice, these accelerators show low hardware resource utilization, so they can't deliver the high rendering speed. On the bottom right, you can see an example. It shows that when HTPU runs sparse JAM operations, only a small number of map units are actually active. Based on what we've seen so far, our goal was to design a new architecture that can efficiently support various levels of precision and sparsity, and overcome the low resource utilization problem of existing JAMV accelerators. Let's go over the design requirements. Let's start with why existing JAM and JAMV accelerators don't use resource well. It mainly comes down to sparse data. So we decided to try something different. That is, we skipped the zeros and mapped only the dense values. To do that, we first mapped one matrix, as shown in the figure on the left. Then we mapped the corresponding values from the other matrix, as shown on the right. What we noticed is that data need to move across both rows and columns. This led us to an important insight, which is to fully utilize the main unit, we need a distribution network that supports flexible data flows along row and columns. Next, to support different precision levels caused by quantization, we used a B-scalable main unit. But this design comes with a challenge. The input data paths with changes depending on the precision mode. As you can see in the figure at the bottom left, This unit is made of 4-bit multipliers that can work together to handle 4-bit, 8-bit, and 6-pin operations. In higher precision mode, some multipliers work together as one, so the input bit widths actually get similar. That's a key structure feature of the bit-scalable multiplier. From a hardware designer's view, we could just design for the widest data path, but that would increase the chip area. In the bottom right image, you can see a cross-section of an actual chip. In this figure, the bottom part shows standard cells like AND or OR gate, while the upper part shows the metal layers used for wiring. When data path widths increase, those metal layers take more space, which leads to a larger chip area. So if we want to make a chip smaller, we need to keep the signal widths as narrow as possible. Based on these requirements, we proposed a new architecture. First, to support dense mapping of data, we use a hierarchical mesh structure that supports multiple data flows. But we added feedback passes inside the mesh. This lets data move between MAC units. With this feedback loop, if a value needs to move to another unit, it doesn't have to go all the way back to SRAM. However, mesh networks usually support data movement in only one direction, either along rows or columns. But our goal is to support flexible data flows in both directions. So we organized the network in a hierarchical way to support both row and column flows. The top level handles column-wise diverse data flows, and the bottom level handles row-wise diverse data flows. With this structure, data can flow in both directions, and MAC units can share data flexibly. Now let's take a look at another MAC structure we propose. As I mentioned earlier, the wider data path can increase chip area. So to reduce the data path widths, we applied pipeline. But when we pipeline the data path, data gets delayed by the number of pipeline stages. In high precision mode, like 8-bit or 16-bit, each column in the bit-scalable MAC unit receives data through broadcast or multicast. So to avoid unnecessary delay in those cases, we added a non-pipelined bypass path as shown in the figure. This allows data to be forwarded directly when needed. Now, let's take a look at another NOC structure we propose. As I mentioned, so another feature we explored in FlexNeRFer is the use of sparsity formats. This means compressing data by keeping only non-zero values and their positions. To get the most benefit, FlexNeRFer stores data in the smallest possible format. One interesting thing we found is that in the bit-scalable MAC array, the precision mode also affects which format is best. This is because the number of active multipliers changes depending on the precision in the bit-scalable MAC array. The figure at the bottom shows how FlexNeRFer detects the sparsity ratio and uses it together with the precision mode to compress data in the optimal format. To compute the sparsity ratio, hardware dynamically checks in real time how many times data is fetched from SRAM, how many elements are in its fetched data tile, and how many of them are non-zeros in real time. Here is the overall architecture of FlexNeRFer. It includes a RISC-V based controller and on LPDDR3 memory systems. And also it has the Jeik accelerator and the neural encoding unit. Now let's look at the evaluation results to highlight the benefit of our design. We compared it against several baseline back arrays used for Gem and Jeik acceleration. The baselines include one that supports only multiple precision, one that supports flexible data flows for flexibility, and one that combines both features. Although our design consumes more power due to the extra modules for supporting both precision and sparsity, it achieves the highest energy efficiency thanks to much higher resource utilization. And this slide presents an architectural comparison. The top figures compare FlexNeRFer with commercial mobile GPUs. As you can see, FlexNeRFer consumes significantly less area and power. The bottom graphs illustrate performance and energy efficiency under various precision modes and sparsity levels. FlexNeRFer constantly achieves better results than the GPU. We also compared FlexNeRFer with a state-of-the-art NeRF accelerator UREX. UREX is designed for a specific NeRF model and does not support quantization or sparsity. As a result, UREX achieves 2 to 47 times lower energy efficiency compared to FlexNeRFer. To sum up, in this work, we analyzed the design requirements for accelerating NeRF models and proposed a flexible network on chip to support them efficiently. FlexNeRFer meets the strict area and the power limits of AR/VR devices, and it outperforms both GPUs and the recent NeRF accelerator in performance and energy efficiency. That's the end of my presentation. Thank you for listening.